Okay, good morning. So yeah, we've got chapter 5, and let me just see here. Chapter 5, where's my syllabus? We've got volumes, area, arc length. Oh, I gotta do arc length, okay. And wow. Yeah. So with with a few of these topics, I kind of gotta like brush uh, over. It's just I'm gonna cover some of these briefly because you don't really need them uh, later on, and I just don't understand the logic behind the department having us cover section 6.1. This is math 8. I don't know what it's doing here. I spent a day in math 8 going over this section. Yeah, this is just the beginning of math 8. I don't know what it's doing here, but I mean, I will go over this section, but I'm not gonna test you on it. I will go over it briefly. Yeah, but let's just do the fun stuff for now. Section 5.1 is actually a fairly long section because we are doing both area and volume in that section. So you're like, hey, we've already done area bounded by curves in a curve and the x-axis. Yes, we've done it. We've done it using Riemann sums, and it's defined as the definite integral from a to b. That gives you area, but we're going to be looking at area between curves, okay? The idea is the same, pretty much. So let me go over just a basic version of this. Let's say we have a function. So here let f of x be non-negative because we're going to evaluate area. We want the function to be non-negative. Because if the function is negative, then the Riemann sum becomes negative and you don't have area. You have net area, but it's not area. So let it be non-negative and continuous on the interval from a to b. Here is a, here is b, and the goal is to find this area here. And again, this area is the definite integral of the function using Riemann sums. So here is a quick approach to get the derivation for area, get the formula for area. So what you do is, just like before, you would be partitioning this region. Okay, this is the region. This whole thing is the region. We partition it. Okay, and again, so, well, I don't think I call the region anything, but I'm going to be referring to regions by R. So here we need the area of the region. Again, I'll be referring to regions as R, bounded by the graph of f of x and the x-axis from x equal to a and x equal to b, to x equal to b. Okay, so here is again the region This is the region R. Yeah, so again, you would do a Riemann sum, taking partitions, doing all that stuff. But here is just a quick way to derive the area formula. All right, so what you do is take a, what we call a rectangular strip, like this. Very tiny one. Okay, well, I am kind of exaggerating on the width of this rectangle, but this rectangle is chosen so that its width is extremely small. It's infinitesimally small. Okay, and call the length, call the width, this width right here, call it dx or delta x. Dx, a differential, it is a very, very tiny delta x. So that's from here to here. We call that dx. Okay? Yeah, delta x is equal to dx for delta x being almost equal to 0. For a really, really small delta x, we just call it dx. And the length of this rectangle, the length of this rectangular strip is the same as y, because this point is on this graph. Therefore, we call the length of this y, or f of x. Okay, so the area of the rectangular strip is basically, again, length times width. And length is f of x, width is delta x or dx. Okay, this is the length of the tiny rectangular strip. So we call it dA. Not A, but dA. Again, just think of D as an increment, a small amount. Okay? Yeah, so the area of this rectangular strip, we call it dA, and it's obtained by multiplying the function by delta x, length times width. Okay? And again, we have infinitely many of these rectangular strips. There are infinitely many of them because this dx is really small. And what you do is you add them up. You add up their areas. Adding up is taking a limit of the Riemann sum, which gives you the integral from a to b. That's the total area. It's the integral from a to b of f of x dx. Think of this as summing all these areas, okay? So again, the integral of f, as long as f is positive, gives you area of the region bounded by the graph of f, the x-axis from A to B. Okay, nothing surprising. We already knew this. Okay, so let's say we have a region that's bounded by two graphs. Okay, so we have a function f of x and another function g of x below f of x. Okay, so I am assuming that g is below f. So here assume f and g are continuous such that g of x is less or equal than f of x on the interval ab. Okay, this relation has to hold on AB. Now, sometimes F can be lower than G, but not on AB, but it's okay. As long as this relation is true on AB, we're good. Okay, so we are interested in the area of the region bounded by the two functions from A to B. So again, this is x equal to A, and this is x equal to b. And again, this is the region. All right, so let R be the region bounded by the graph of f of x and g of x from x equal to a to x equal to b. So we want the area of that region. You're going to do the same thing. Take a rectangular strip. So let me just take it like that. Again, we are kind of exaggerating on the width of the strip. The width is extremely tiny. All right. So again, the width of this rectangle, if you pay attention, that width is pretty much a small change in x. It's delta x. Or dx. Call it dx. Okay, that's this width. And then to get the height, notice that this point on the rectangle is on the graph of f of x. Okay, so if I choose an x, if this point is, think of it as a sample point, x star I, k, whatever we call it, x star I, or just call it x. I'm not going to use sample points or stars or anything like that. So take a point x. This point, since it's on the graph of f, that point is x f of x. And this point here is x g of x. Okay, so let me draw that rectangle right here. Yeah, so again, the length is, this length is dx or delta x, and the height is basically the difference of the two y values. You take the top y value minus the bottom y value. Imagine the y value for this point is 5, and the y value for this point is 2. So the length of that rectangle would be 3. You just do f of x minus g of x. That's this length. Okay, so here dA, the area of that rectangular strip, is going to be length times width. Length is f of x minus g of x. The width is delta x or dx. And then we're going to sum up the area of all rectangular strips. There are infinitely many of them that partition the region like that. You want to add them up. That's the same as taking the definite integral. Okay, so this is the area of R. If you see R as a subscript, that means region. Area of the region is the integral from, again, A to B of dA. Okay, so that's how you get the area of the region. First subtract, just do the integral of the difference of the two functions as long as the top function is top, right? As long as this is the upper function, this is the lower function. Okay, if this inequality is not true, then you're gonna end up with probably 0 or a negative area, and that makes absolutely no sense. Okay, so the integrand has to always be positive. If you want the integral to represent area, this integrand has to be positive, meaning that f has to be more than g. Okay? Yeah. And again, guys, we need continuity, because if continuity doesn't hold, then the fundamental theorem is not going to work. Fundamental theorem requires function to be continuous. The proof required continuity. Imagine there is a vertical asymptote right there. If there is like right here, if there's a vertical asymptote, then this area is gonna go forever. I mean, how do you find the area? It could be infinite. So we don't want anything funny to happen. Okay, so let's do a problem. Find the area of the region bounded. You know what that means. Bounded means bordered by. Graphs of f of x equal to, or I could just call it y. Let me call it y. Y equal to 5 minus x squared. And just because I wrote that function in blue, it doesn't mean it's a bigger function. You have to identify that on your own. And g of x equal to, let's see what to go with, or y equal to x squared minus 3. Okay. And notice that this problem is not telling you what A and B are. It doesn't tell you from 1 to 4 or from -1 to 1. You have to figure that out on your own. Okay? And fortunately, you have to graph these. You gotta graph these functions. This is why we learn graphing. Okay? And thankfully, by fortunately, I meant to say that the graphs are not that difficult. These are just typically a few easy polynomials that you have to graph. Okay, but that is a must. You must graph the region. Okay, because if you don't graph then you wouldn't know which function is the top function, which is the bottom function. You don't know what the limits of integration would be. Okay, you need to find those. You need to see where the region begins and where it ends. Okay, so we need to graph them. And you have to, again, you have to have some idea of the graph of these functions. These are both parabolas, okay? And the difference between the two is that this graph, this parabola opens downward, but this opens upward. Downward, upward. Okay, so please try to imagine the region in your head, or just do a really quick sketch like what I'm doing here. This would be the region. Okay, if you look at the bounded, the area between, it's that. Okay, and this area is going to begin right there at that point, and it's going to end at that point. So if the problem doesn't tell you where the region starts and where the region ends, you need to find the points of intersection, those points. We need to. It's going to make your life easier. It's going to give you the limits of integration, and it's going to help you with the graph. Okay? Tremendously help you with the graph. So, step one, if no A or B is given, these are the endpoints, then find the points of intersection. Of the two curves. Okay? By just setting them equal, that's all you're doing. Right? This graph and this graph are equal. They intersect where their y values are equal. Okay, so just set them equal by setting the functions equal. So we just do 5 minus x squared equal to x squared minus 3. And this gives you a fairly simple quadratic equation. It's not that bad to solve. Move the x squares to one side. You end up with, let's just move the x squares to the right. You get 2x squares, and move the constants left. Move the negative 3 over. It becomes 5 plus 3, which is 8. That gives you an x squared of 4, which solves to x equal to plus or minus 2. We expected to get two solutions because we have an A and we have a B. Okay? Yeah. And if you want, get the y values, because we're gonna be plotting these regions. We're gonna graph the region, so it's better that you get the y values. So just plug positive, negative 2 into either this equation, this function, or this function. It doesn't make any difference because plus minus 2 makes both these equal. So points of intersection, x equal negative 2, y is equal to, yeah, just plug it in here. Negative 2 in there, it gives you y 5 minus negative 2 squared, which is equal to 1. Okay, and if you put positive 2 in there, you also get 1. And again, as I said, it doesn't matter which of these you plug in. If I plug negative 2 into this, negative 2 squared is 4. 4 minus 3 is 1. Okay, so graph R, graph the region. And it's fairly simple, again, to graph these parabolas. But let's just look at points of intersection. We have -2, -2, 1, and 2, 1. Those are the intersection points of the two functions, okay? And graphing these is hopefully effortless. This is, again, a parabola shifted up by 5, and it's concave down. It's opening downward because of that negative. So the vertex is 1, 2, 3, 4, 5 right there. Here's a graph of that function. Again, a parabola. Okay, so that's 5 minus x squared. And then the green function is shifted down, parabola x squared shifted down by 3. So vertex is going to be at 0, -3. And again, it's concaved up because the leading coefficient is positive. And it's going to cross those, pass through those intersections, points of intersection. So this is it. Okay. Please shade the region. Don't forget that. Your objective. We are finding the area of the bounded region. There is no other region that can be bounded, guys. If I were to continue with these graphs, right, like there is nothing here that bounds. This is an unbounded thing. It will go forever, okay? There is no area between these. There is no, I should say, region between these. This region is infinite. Okay, this is the bounded region. A bounded region has boundaries, okay? It has boundaries. It's surrounded by curves. Okay, so this region, this is not bounded because there is nothing that bounds this side of the region.
Professor?
Yeah.
Question. So do we have to plug in the points of intersection into only one of the equations? Like here you chose to plug it into 5 minus x squared, but could we have plugged it into x squared minus 3?
Yeah, and I did that. I got the same thing. And I mentioned that it doesn't matter where you plug these in because we set the two functions equal. Okay, so the two expressions are the same at -2 and 2. So it doesn't matter if you want to plug here or here. You get the same thing. And I tried, right? If I plug -2, but -2 squared minus 3 is 4 minus 3, that's equal to 1. Get the same thing. Okay, so we are ready to set up the integral. Again, if you want to take a rectangular strip, so this is the area integral. If you want to take a rectangular strip, be my guest. Here it is. Okay, and let me actually do the setup over here. Okay, so that's a strip. And again, this is the width, which is delta x. And the length is, again, the top function minus the bottom function, which is x squared minus 3. So area here is equal to the integral that goes from -2 to 2 of the top function, 5 minus x squared. That's the top. Minus the bottom. Always top minus bottom. X squared minus 3. And yeah, so we are about to calculate this integral. Therefore, you want to take advantage of symmetries. You should. You could see that this region is symmetric with respect to the y-axis. So I can instead integrate from 0 to 2 and double that area. Okay, so area is equal to the double of the integral from 0 to 2. And while we are at it, let's add like terms within the integrand. So here we have 5 minus -3, that's 8. And I have -x squared minus x squared, -2x squared. There you go. So again, I did two things. I took advantage of symmetry and I combined the integrand like that. So this is since R is symmetric. Okay, if you don't do all that, it's fine. If you don't want to take advantage of symmetry, it's okay. The answer should still be the same. Okay, and then step 4, calculate. Now, on the exam, if time is short for certain problems, I just have you set up the integral, okay, without evaluating the integral. For some of the problems, I might do that. So just keep that in mind. Okay, so the area of the region, that subscript means area of region. So let's calculate the integral. We have the 2 sitting in front. That 2, just leave it out. Find the antiderivative. Antiderivative of 8 is 8x minus antiderivative of x squared is 1/3 x cubed. So you got 2/3 x cubed running from 0 to 2. See, the wonderful thing about taking advantage of symmetry is that when you plug 0 into these, you just end up with zeros. And you don't have to do a lot of calculations. So evaluate. Plug 2 in. You get 8 times 2 minus 2/3 times 2 cubed. Plugging 0 in, you just get 0. Okay, so what we get here is 2 times 16 minus 2 cubed is 8 times 2, that's 16. 16/3. Okay, and then 16 minus 16/3, that's 32/3. 32/3 times 2, 64/3. And it's a square unit. Don't forget the unit of area. Okay, it's square unit. That's it. Okay, questions? Fairly simple problem, hopefully. Yeah, this is fairly simple to what's about to pop up. Yeah, so sometimes we have what's called a compound region. And for that, we have to be careful with the graph and how we set up the area integral. Okay, so a compound region is a region where the boundaries, the top and bottom boundaries are not always consistent. The top and bottom boundaries are just different sometimes. Okay, so for instance, let's say we are looking at this region. Look at that region, the area between those three curves. Okay, so if you notice for this sub-region, like until here, the top function is this curve. Okay, it's this right here. This is the top function. But then after this point, the top function is going to be different. Top and bottom may not always be consistent. Okay, let me just do an example with numbers. So this is example of compound. So in a compound region, again, the top or bottom boundaries are not consistent. All right, so let me do an example. Let's say you want to find the area of the region bounded by graphs of y equal to negative x squared plus 3x plus 6 and y equal to absolute value of 2x. Okay. All right, so we've got a parabola. So let's try to imagine this graph. We have this parabola. Is it opening upward or downward?
Up. It's
Downward.
Opening
Because it's
up.
negative.
Downward, yes, it's there is a negative here. And whenever the leading coefficient is negative, parabola opens downward. Okay, also you can think of the second, to use the second derivative idea. The second derivative of this function is negative. If you take the derivative twice, you'll end up at -2 for y double prime. So it's a concave down. This graph is concave down. We have a concave down parabola like that, and we have an absolute value graph. We all know how to graph absolute value like that. Okay, so this is what you want to do. Try to imagine the region or do a really quick, dumb sketch of the region. Don't spend so much time. Just do it like that, like that. V-shaped parabola. That's the region. Okay, so it's going to have intersection points right there and there. Okay, and we're going to find them. Let's find the intersection points. So step 1, points. Okay, guys, so I need to again set this equation equal to this equation. And don't yet panic and say, oh crap, I got me an absolute value. an equation that involves absolute value. That's fine. We all know how to deal with absolute values. Absolute value of x means plus x or minus x, as easy as that. Okay, but set the two functions equal to absolute value of 2x, like that. So this is gonna, look, in many cases, by the way, you could just solve by inspection also if you want, but this can easily solve, okay? Again, don't panic. Say, I haven't seen anything like that. Again, this breaks up to two equations. Yeah, it's gonna do that. You're gonna get an absolute value of x, and then let's just break it up. So we have negative x squared plus 3x plus 6 equal to negative 2x. That's one equation. Or you're going to get negative x squared plus 3x plus 6 equal to negative of 2x. Okay, again, absolute value of 2x. Oh, I meant to say positive of 2x. Absolute value of 2x means negative 2x or positive 2x. Okay? Yeah, so this first equation is true. This, guys. This is true if x is less than 0. And this equation is true if x is more than 0. Does that make sense? Because of the definition of absolute value of x. Remember, absolute value of x is equal to positive of x if x is positive, negative of x if x is negative. Right? And it doesn't matter if there's a 2 in front. We all know how to deal with absolute. We've done plenty of them. Okay, so solve this equation. And remember that the solution of this equation is gotta be less than 0. Okay, so let's see how to solve this. Just move everything over to one side of the one side and set equal to 0. Let's move everything to the right. I'm gonna move all of that, all of this to the right, because I want that negative x squared to become a positive x squared. Okay, so move to the right, you got positive x squared. Move this to the right by taking it away. Subtract the 3x, you get minus 5x. Move the positive 6 to the right, it becomes negative 6, set that equal to 0. And to be honest with you, the hardest part of these problems is setting up the integral and finding the points of intersection. It's not the calculus that's hard. It's the algebra, as I've been saying over and over. We can factor this thing out. You get x. Can we? Yes. X minus 6, x minus 1, or x plus 1 equal to 0. And this gives us two solutions, x equal to 6 and x equal to...
If you're adding 2x, wouldn't that be 5x? Positive 5x?
Yes, you're right. So no, I am moving things to the right.
Oh,
so
okay.
That you're taking away a 3x.
Okay.
You could move this to the left if you want, but then I don't want to deal with the negative x, you know? It's up to you how you solve these, just do it right. Okay, so guys, I got two solutions. One of them is no good. Which one?
6.
Yes, this is a positive solution. And I don't care for it because because we are on the domain of absolute value where x is less than 0. Okay, x less than 0. So I take that out. X equal to -1 is the solution right there. Okay, again, x.
But then,
yeah.
sorry, on the opposite side, then would you throw out -1 if x is greater than 0
Yep.
and you keep the x? Okay.
Yeah. Let's solve this equation. Let's see. Did you get 1 when you solved it? So move all of that over to the right, just like what we've done here. You get positive x squared. Okay. Move this away. Subtract 3x. 2x minus 3x is -x. Move the 6 over. It becomes -6. Set it equal to 0. Factor it out. You get x minus 3 and x plus 2. That gives us two solutions, x equal to +3 and x equal to -2. Which one of them is valid?
3.
-2.
So this says x has to be, positive. I don't know if I answered your question correctly, but
Yeah, so you throw out -2, right?
yes, I throw out the -2. Yes, so it has to be, because x has to be positive. So that goes away. And we just found ourselves points of intersection. Okay, and this is probably the hardest thing to do, because if you have the points of intersection, then you can easily graph the function. So let's see if I can graph them. Okay, so I'm gonna locate the intersection points, -1 and 3. And to be honest with you, it just takes almost no effort to graph these, because we have an idea, we do have a good idea what these graphs look like, right? We do. So let's go with the easier graph. I'm going to go with the easier graph, which is the absolute value of 2x. Okay, absolute value of x is the V shape. We just have 2 in it. And it's going through these points. It's going through the points of, oh, by the way, let's get their y values. I didn't get those. Let's get those y values. So points of intersection, x equal to -1. Now to get me the y values, I can take -1, plug it into either this blue function or the green function. It doesn't make any difference, because at these points, the two functions are the same. It doesn't matter where you plug these. Plug it into the absolute value one. It's easier to get. Y here is equal to absolute value of 2 times -1, which is just 2. Okay, so 1 point of intersection, -1 and 2. Right there, we have 1. And the other point of intersection, plug it into either function, 2 times 1. That's also 2. Oh, I'm sorry, guys. I meant to plug in 3. Sorry. I meant to plug 3 in. Okay. When x is equal to 3, y is the absolute value of 2 times 3, which is equal to 6. So 3, 6. Is all the way up here. Obviously, we do not have any symmetries going on. Okay, so you can check. You can plug -1 into the quadratic function, and I promise you, it will give you 2. Don't believe me? Let's do it. -1. Plug it here. Okay, so -1 squared there. Here, let me just do it. -1 squared is +1 with the negative in front. So we get -1. 3 times -1 is -3 plus 6. -1 minus 3 is -4 plus 6. That's equal to 2. And that's exactly what we have here, 2. That's how you can check to see if you've done your equation correctly. Okay. All right. So again, let's graph them. Graphing here is easy as long as you have your intersection points. Let's graph the green function. This is the V graph, and it's going through the points of intersection. Okay, so like that. You don't have to graph the whole thing. If you want, you could graph more of it like that. Okay, but again, I don't need the whole thing. And then the quadratic, well, I know that this quadratic is, again, it's concave down, and it has to go through those 2 points. Okay? It has to go through those 2 points. So how else am I gonna draw it? Honestly, like how else am I gonna draw the quadratic function? I mean, I could draw it like that. No, that's weird. Let's see. Just draw a parabola concave down, going through those 2 points. Okay? I mean, you can locate the vertex if you want, but it doesn't matter. Okay? Blue. So there. This is perhaps not the correct graph, and it's not because I don't know exactly where the vertex is. I can find the vertex, but it's irrelevant. The vertex is irrelevant. Okay, so our region is this. And the easy part, again, is the calculus part. Okay, so, oh, well, yeah, the easy part is the calculus part. But this region is a compound region, okay? I take it back, I said easy, because I forgot that this region is compound. All right, so let's see. Let's see how those, how the rectangles set up, those rectangular strips. So guys, please pay attention. If you take a rectangular strip, the length of the strip is not always the same. Guys, it's not. Because I can draw a strip, let's say here. Okay, the top function for this strip, the top function is the parabola, but the bottom function is this line. Okay, whereas if I draw another strip, like let's say here, right there, the top function is the parabola. So no matter where you draw the strip, the top function is always the parabola. But the bottom function is now this line. It's a different piece. Okay, and we can get the equation of these lines. This line is basically y equal to 2x. And who can tell me what is the equation of this line?
Minus.
Y equal to -2x. Okay, so from below, the region has two different borderlines. Okay, this is one borderline, and the borderline changes right here over this subregion. There are two subregions, this one and this one. So what you have to do is when you set up the integral, you have to write it as two integrals. One integral that goes from -1 to 0 for that subregion, and then another integral from 0 to 3 for this subregion. Okay, and I'm gonna use a different color here. Give me a second. For this region. So call this region R1 and call this one, the pink one, R2. Okay, so area of R1 is equal to the integral from -1 to 0. Again, this region runs from -1 to 0. Okay, and the length of that rectangle, the length of this rectangle is the top function, which is the blue function. And the equation for it is -x² plus 3x plus 6 minus the bottom function. And the bottom function here is -2x. Let me actually just move this down here. And let me just write both integrals. Okay, so again, we're going to take the area of the two region R1 added to the area of the other region R2. Okay, so again, this is going to give me the area of R1. And then to get the area of R2, same thing, you do a Riemann sum or find a definite integral. Can anyone tell me the bounds of integration for this integral? Where does it start and where does it end?
From 0
Yeah, to what, guys?
to 6.
To 3.
Oh, no, to 3.
From here to here. Okay, and again, for this rectangle, the top function is the blue graph. So same thing, -x² plus 3x plus 6 minus the bottom function is 2x. Okay, this is how you set up the integral. But please watch out for for any inconsistencies throughout the whole region. The top and bottom, we have consistency if for any rectangular strip, the top and bottom don't change. Okay, like what we have here. No matter where I draw my strip, the top is the blue graph and the bottom is this graph. Okay, but for this graph, the top is always the same throughout the region, but the bottom bound changes. Okay, sometimes it's that, sometimes it's that. So this integral, these two integrals, a lot of work, guys. This is an example where I would ask you to just leave it alone. Okay, I would say give an integral representation of the area of the region, and you just leave it like that. because the rest of it, the rest is basically math software can do these integrals. It's a lot of arithmetic. So
Is that it's supposed to be negative x on the right too?
negative x on where?
The right side when you added it, is it supposed to be a positive x square?
Here?
Yeah.
Why? Why should it be a positive x squared?
Oh, never mind.
This graph is just it doesn't change. This is the graph of y equal to negative x squared plus 3x.
Yeah, I thought that was the absolute value one, but no.
No, yeah, this is the absolute
Yeah.
value one. Absolute value of 2x is negative 2x and 2x. This
Okay.
is just a quadratic. Yeah, so we can leave the answer in integral form if asked. If I ask you to leave the answer in integral form, this is it. That's the answer. Okay. So let's do one more of these. Let's just do one more of these examples because they are kind of important. And there's a shortcut for them also. So here we want to find the area of the region bounded by a graph of y equal to x to the 2/3 and y equal to x minus 4. Okay, maybe I can make that a square root of x because it's easier to graph. Yeah, let's just do that. Let me make sure that these actually solve. If I want to find a point of intersection, so what would be a good, let me see. If I were to set these two, I just want to make up the problem so that it works out. You know what I mean? So give me a second. I don't want to throw a problem at you that's numerically difficult to do. So give me a moment. Okay, I found it. X minus 2 is better. Yes. Okay, much better. All right. So let's imagine, guys, let's picture the area again. Let's do a rough sketch. So again, step 1. We're going to graph these, but we have to find a point of intersection. But again, I need to know, we want to have an idea of the shape of the region. So square root of x is that graph. Okay, we all should know what square root looks like. x minus 2, that is a line, and the y-intercept of x minus 2 is negative 2, so it looks something like that. Okay, so the region, and I'm gonna write down, by the way, in the first quadrant. In the first quadrant, I will write it down also. So the region will be this right here. Okay, this is what I'm looking for. Let me write down the rest in quadrant 1. Okay, so one more time. That's the square root. This is a graph of x minus 2 in quadrant 1. This is what we are interested in. Okay. So the point of intersection of the two graphs is gonna be right there, somewhere right there. Okay. When you set these two equations equal, I'm gonna get a solution that's positive. So let's set them equal. And if you have an equation that looks obnoxious, this equation is not that obnoxious. You can easily solve it. So what would I do to solve this? I would have to square, because I have a square root. Just reasonable to get rid of the square root by squaring. Okay, that might take a little bit of work. So I would call this equation probably a little bit obnoxious. And when that happens, you can always solve by inspection. I don't care. I don't care about the algebra. Solve by inspection. Just plug in what works. What do you think works? Okay, and we know that there is one solution. This thing is going to have one solution. It's right there. Somewhere right there, maybe 1, 2, 3, 4. I don't know. Just plug values.
It's 4.
And see. 4 works. Just try out values. Trust me, these equations are not going to be, they're not going to have crazy irrational solutions. It's a reason they're going to have reasonable solutions. Okay, so yeah, by inspection, x is equal to 4. Because if you put 4 here, you got 2. You put 4 here, 4 minus 2 is 2. 2 is equal to 2. So that's a point of intersection. Now we can graph. And it's in quadrant 1. So I don't care about this part of the plane. Okay, graph the square roots. And by the way, you could get the y values. So x is equal to 4. And here y is equal to, plug 4 into here or here. It doesn't matter. Either way, you get 2. Okay, so 4, 2. Is point of intersection. Okay, and here is the graph of the, let me make these a little bigger, guys. Let me make the y values a little big.
Professor, if we solve the equation equal, we will get the 4 also, or no?
Yeah, of course you will. Yeah, square. You have to square this. You have to square that. And then you got a quadratic, move everything to one side and solve. Yeah, you will.
Thank you.
Mm-hmm. Yeah, why? I mean, if we solve and we didn't get 4, then that's a huge contradiction. That couldn't happen. Okay, so graph the line. We know again this point is on. this point of intersection. 4, 2 is also on the line. So you can pick one more point on this line. For instance, I can choose 2. Okay, if I choose any point to graph this line, I'm gonna choose 2 because 2 makes this 0. So right there, this point is on the graph. The graph of the line is that. And again, I don't care about the whole thing. I don't care about this part because the region is supposed to be in quadrant 1. So again, this is the region. Okay, but this region, I shouldn't be shading it yet because it's compound. It's a compound region. Why is it compound? Throughout the region, the top or bottom boundaries are not consistent. Okay, so if you notice right here, if I draw a rectangle like that, the top is bounded by the blue graph, but the bottom is bounded by the x-axis. See, let me first of all erase the whole thing. Yeah, so again, right here, here is a rectangular strip. The top is on the graph of x square root of x. The bottom is on 0, 0. I'm sorry, it's on the not 0, 0, it's on x 0. The y value is 0. Okay, whereas if I draw a rectangle like that right there, the top is just like before, this point is x root x, but the bottom is going to be on the green graph, which is x minus 2. So you see what's going on? The top boundary is always consistent. The top boundary is always root x. But the bottom boundary is sometimes this line, sometimes this line. We don't have that consistency. Okay, so we have to break this up into 2 integrals. One integral goes from 0 to 2. This point is 2. And then we have to do another integral from 2 to 4. Okay, there are 2 subregions. This is one of them. And this is the other one. Guys, make sure you understand that, please. Okay, so let's do an integral from 0 to 2. Okay, this is the area of the first region. The length of this rectangle is top. The top function is the blue function, which is root x, minus the bottom function. The bottom function is just 0, right there. Okay, so that's what's happening from 0 to 2. From 0 to 2. This gives you the area of this region, right there. Okay, and then from 2 to 4, the top function, again, for this rectangle, the top function is root x minus the bottom function is the green function, which is x minus 2. Don't forget that thing is in parentheses. dx. Okay, so the total of these two integrals gives you the area of the whole region, the whole thing. And again, I'm gonna just leave it like that. You could go ahead and do the integral, but we'll just leave it for now. If you were to actually do this integral, you should get 56 over 5. Okay, the value of this integral is 56 over 5. Now, when we come back from the break, I'll show you a more quick way for finding the area of the same region. Okay, what if you're asked to find this integral, find the actual area? Instead of doing two integrals, we can do just one integral. There is a shortcut, and that's when you change what you integrate with respect of. I'll show you after the break. So take a 15-minute. I am recording. Yeah, and I really, really do need you guys to be here, because if you're not looking at this, it's not going to be easy trying to learn this on your own. Yeah, well, who said that you have to take your rectangles like that? So you're kind of like taking this region and you're cutting it into pieces like that. And you're finding the area of those pieces and you're adding them up by integrating. Who said that you have to cut? Take scissors and cut like that. You can cut like this. We can. We can take our rectangular strips, horizontal or vertical. I've taken a vertical so far. I can take them horizontal. And that gives us a different kind of integration. It's integration with respect to y. So let me discuss that a little bit. And you have to know both ways. Okay, so let's say that we have two functions, but these are not functions of x's. These are functions of y. For instance, you have seen a sideways parabola, probably. This type of parabola. The equation of this parabola is x equal to y squared. It's not y equal to x squared. It's a function of y. This is not a function of x. It can't be a function of x because it's going to fail the vertical line test. This is a function of y. You're just switching your x and y, pretty much. But I can have so let's say we could have this graph. See, it's kind of harder to wrap my head around. This graph, it's x a function of y. X is equal to f of y. And we could have a left graph like this one. It's x equal to g of y. X is also a function of y. And assume that x goes from C to D. I'm not going to use A and B because I used A and B for when I did integration with respect to x. A to B, x goes from A to x equal to B. Since I'm doing integration with respect to y, I'm going to call my y values y equal to C. This is y equal to D. So let's say This is the region. Now, all right. So what we do is we take a rectangular strip that's horizontal, like this. And we use the same idea, but the thing is that the width of this rectangle is not, it's not dx anymore, it's dy, because this is a vertical change. You see that? That is a vertical increment. It's a delta y or a dy. Change in y. That's what that is. Okay, and so again, this point is on the graph of, here x is f of y, and y is just y. And this point there is on the graph of g of y, y. Okay, here our x is described as a function of y for every y value. So if you're finding the, let me draw that rectangle here. That, so if you're finding the, again, this is dy or delta y. If you're finding the length of this rectangle, it's going to be the right function minus left. It's the bigger x minus the smaller x. It's f of y minus g of y. Imagine this x is 5 and this x is 3. So you do 5 minus 3, that gives you 2. Again, you take this x minus this x. So that length is going to be f of y minus g of y. And we are assuming here that f is bigger than g. We have a right function, we have a left function. So area here is equal to length times width, length f of y minus g of y times that by width. The width is dy. That gives you, again, the area of this rectangle. And then you're going to do a Riemann sum. Add the area of all rectangles. That's basically the integration going from C to D. You're adding all of these, the area of all these horizontal strips. Yeah. The sum of the area of the horizontal strips. That gives you, again, an integral with respect to y. It sounds kind of weird, but it can be done. And it can be done on especially on the previous example. It's gonna make our previous example a lot easier. So we're gonna revisit this example. So yeah, we have y equal to square root of x. And y equal to x minus 2 in quadrant 1. Okay. And I've already found the points of intersection. So step 1 is the same. It's the same as before. Graph is the same as before. Nothing changes about the region. We're just gonna re-express the bounds a little differently.
Professor, here we have to change x and y.
Yes, I'll get to that. Okay, let me just grab. Okay, so our point of intersection was 4, 2. Let me look at that. Goes through 1, 1. Just copy the region down from the previous question. Okay. All right. So guys, look, the good thing about doing this type of integration on the region is because if I were to take my rectangles, so again, one more time. Again, this is really important to understand because this can make the amount of work much less. It's more learning, I understand, but it's going to cut down the amount of work. It's basically a shortcut to this whole problem. It's meant to make the procedure easier. So one more time. If I were to take my rectangular strips vertically, the length of the rectangle wouldn't be consistent. Again, sometimes the length of the rectangle is going to be the blue graph minus the x-axis. Other times, the length of the rectangle is going to be the blue graph minus the green graph. And that's why you had to do 2 integrals. But now, if I were to take my rectangles horizontally like that, the question is, what's the right bound? What's the left bound? No matter how I draw my rectangles, the right bound is the green graph and the left bound is the blue graph. It's always the same. Look, right there. If I draw a rectangle, on the right, it's the green line. On the left, it's a curve. If I draw the rectangle here, on the right, it's line. On the left, it's a curve. Those rectangles have consistent length. So you just need to do one integral from 0 to up to this point, which is 2. We have that consistency. Okay, so here is a rectangle. Rectangular strip, kind of. Okay. And if you want to get the length, it's going to be this curve minus this curve. It's going to be this x value because this is horizontal. Since this is horizontal, you have to find the difference between the 2 x values. Okay, between the 2 x values, not y values, but x values. So how do you get x? Well, you go back to your curves and you're going to express these, or you're going to solve these for x. They're solved for y. You need to rewrite them in terms of x. Okay, so express each equation, or solve each equation, I should say, for x to express it as a function of y. All right, so, and it's really straightforward to do that. If y is equal to root x, and I'm solving for x, all I gotta do is just square. Okay, this gives me x equal to y squared. X equal to y squared is a sideway parabola. And this is what a side, it's a part of the sideway parabola. It's opening to the right. So this x is y squared. And if I want to find what this x is, I solve this relation for x. That gives me x equal to y plus 2. So the equation of the green line is going to be x equal to y plus 2. This is still a line. It's just that we are expressing x in terms of y in terms of expressing y in terms of x. Okay? So the length of this rectangle now is going to be always the bigger x minus the smaller x. So right, it's the big X minus the small x. And the big X is this, it's y plus 2. X is equal to y plus 2. So y plus 2 minus the small x is this one, and it's given by y squared. Okay, so that's the length of the rectangle, and it's in terms of y. And again, the thickness or the width, not thickness, the width here is dy. This is dy because it's a vertical change. So if I want to find the area, area is going to be length of the rectangle, which is y plus 2 minus y squared. That's length multiplied that by the width. The width is dy. And then you're going to integrate from here. Look at this, guys. Your horizontal rectangular strips, these rectangles, begin from here, and you kind of stack them up. You add them up all the way to this point. Okay, so they begin from y of 0 until where y is equal to 2. Since it's integration with respect to y, you have to see where y begins and where y ends throughout the region. Okay, so this gives you area of the region. So if you compare this integral to this integral, we can say definitely this is easier to evaluate. Easier to evaluate. And the answer should be, I did spit out a number. The answer should be 56/5 if you do this. But we can easily evaluate this area. So integral is half y squared plus 2y minus 1/3 y cubed, going from 0 to 2. Plug 2 in. So you got 4 divided by 2 is 2. Okay, plug 2 in here. You got 2 times 2, 4. Minus 1/3. Plug 2 into y. You get 2 cubed. That's 8. So minus 8/3. Okay, so 2 plus 4. That's 2 plus 4, 6. Minus 8/3. 10/3 actually, 10/3. Yes, 10/3. I'm sorry, 56/3 is for a different problem. Yeah, that's the correct value. So 10/3 square unit. Now, as a practice, I don't know if you have this kind of time right now, but you can do this whole thing. Just do it if you have time. And I promise you, you're going to get 10/3. I promise you. This is a lot easier.
You told us 56/4.
Yes, 50. Yeah, that's for a different problem. Yeah, it's for the problem when you so remember how I wrote down this example and I had 4 right there. If I keep that 4, it's 56/3, but I change it to 2, so the answer is 10/3.
Could you technically like graph these and just change up the x and y axis?
What do you mean change the x and y axis?
Because that looks kind of trippy to me, to be honest. 'Cause, like I don't like. It's still kind of weird how y plus 2 is the big X. Because like from like intuitively, I don't know, it kind of looks like y minus y squared is like the big X.
Okay, well, why? Isn't just pick a point. If you don't believe me, pick a point. For instance, if I choose 1 for y, choose 1 for y, okay? Plug that into this function, you get what? You get 3, okay? If I plug 1 into this y, I'm gonna get 3. If I put 1 in here, 1 squared is equal to 1. So which is bigger, 3 or 1? Isn't 3 bigger?
Yeah.
Isn't the green graph bigger? The x of the green graph? Not the y, the x. For the green graph, the x values of the green graph are bigger than the x values of the blue graph.
Okay.
So we have to take this x minus this x. This y plus 2 minus this y squared. Let's do one more setup, and then I have to really move on to the next topic. One more example. Bounded by graphs of y equal to x cubed, y equal to x plus 6, and the x-axis. Okay, so one of them is the cubic function, that's x cubed, and the other one is x plus 6, which is a line. It's gonna look like that. Yeah, so this is going to be our region. Okay, so x cubed and the line x plus 6, they have a point of intersection. Let's actually find that point. Set the two functions equal. We have x cubed, and let me just use colors. X cubed equal to x plus 6. Okay, so again, guys, don't consume time solving these equations. I know that you feel like a nerd when you see a higher order equation like that, and you're like, oh, let me do synthetic division and all that stuff, and that would be impressive. The more impressive thing for you is to be clever with certain things, and this is one of them. So just solve by inspection. Try to solve by inspection. See what makes this true. So let's try. We know, again, the way this draws out, we know that my x has to be positive. Again, this is a cubic graph. This is the line. The solution has to be positive. This x is positive. So try 1. 1 is not going to work, but 2 works. If I plug 2 here, 2 cubed is 8. 2 plus 2 is 8. So x is right away equal to 2 by inspection. Okay, get the y value, plug 2 into any of those, either of those functions. So here point, x is equal to 2 and y is equal to 8. Okay, plug 2 here or 2 here, yeah, 8, either way. That's a point of intersection. And then quickly draw the graph. Okay, so 2, 8 is going to be on the graph. 1, 2, 3, 4, 5, 6, 7, 8. This point is on both graphs. The graph of y equal to x cubed. Again, the S-shaped graph. It goes through 1, 1. It goes through 0, 0. It looks something like that. And again, we don't care about the negative portion of the graph because the region is also bounded by the x-axis. To graph the line or the green function, yeah, to graph y equal to x plus 6, you can choose -6 for x because that gives me the x-intercept. If I choose -6, plug it in there, I get 0. You can plug any point you want to graph a line. You could choose 5, or 5 would be bad actually. You could choose 1. 1 here gives you 7, so 1, 7. That point is on the line. Just draw the line like that. But I'm going to choose -6 because it's easier to draw. -6, 0 as a point on the green line. Okay, so that's the line. And also the x-axis. X-axis is going to bound the region. Okay, so here is the x-axis. The three graphs, the green line, the blue curve, and the x-axis bound the region. So it makes sense for this to be a region. Okay, that's it. That's our region. Now, you're asked to find the area. Okay, you can, again, take your rectangles vertically or you can take them horizontally. it doesn't make any difference. You just have to see which is easier. Okay, let's say I take my rectangles vertically. If I do that, the question is, do I get consistency? And the answer is no, because if I draw a rectangle right there, the top is the green graph, bottom is the red graph. Okay, but if I were to draw a rectangle right there, top is the green graph, but the bottom is the blue graph. The bottom boundary is not consistent. So for this type of integration, you have to set up two integrals. Okay, integration with respect to x requires two integrals. But if I were to draw my rectangles horizontally like that, regardless of where I draw, left and right boundaries are always the same. Okay, here the right boundary is the blue graph, the left boundary is the green graph. Okay, no matter where I draw it, same thing. Right is blue, left is red. Okay, so doing integration with respect to y requires only one integral. Okay, so since we're going to do dy, then you want to solve these equations for x. You want to express them in terms of x. Okay, so let's go with y equal to x cubed. Solve for x, you get x equal to y to the power of 1/3. Okay, so the equation of that cubic function is x equal to y to the 1/3. And then we have the line y equal to x plus 6. Solve that for x. You get x equal to y minus 6. So when I draw a rectangle, horizontal rectangle, like that, the left x, left is the blue, left x is this, right x is this, left x is this. So the length of the rectangle is going to be this function minus this function. Y to the 1/3 minus y minus 6. Okay, this x minus this x. And the width is just dy, that increment change in y. So area of this region is equal to y to the 1/3 minus y minus 6. Okay, so that's length times width, which is dy. Now you're going to do a sum or the definite integral. Okay, these rectangles begin at y equal to 0. And where do they end? Which y do they end at? Anybody?
Y equals
8.
Y equal to 8. Yes. So throughout the region, the smallest y is that, and the largest y is the y for this point, which is 8. Okay, that point to 8. This is why we need the intersection point. It's going to give us the bounds of integration. Yes, what's your question?
I'm sorry, but can you repeat again how you did with the other one? How you told Angel which one did you choose, or why did you choose y and 1/3 to be the bigger one?
It's okay. So when you're taking a rectangle horizontally, right is always bigger than the left, isn't it? isn't right bigger than the left? So on the right, we have the blue function, and on the left, we have the green function, right?
So it's going to be like that always.
Always.
What's on the right is going to be bigger.
Yeah.
Okay.
If
Yeah, that
you're
makes it easy.
if you're taking your rectangles vertically, it's always top minus bottom. Top minus bottom. Top minus bottom. But if you're taking them horizontally, it's always right minus left. Right minus left. If you don't do right minus left, you're going to get a negative value, and that just makes no sense. Okay, and that's it. If you want to do that integral, guys, be my guest. But I have to move on to now the next thing, which is volume. Okay, but this is all you need to know about areas. Make sure that you go with the more efficient method. Unless on the test, I ask you to do integration with respect to both x or y. Okay, but just go with the more efficient. All right, so I'm gonna start a new notebook here. Okay, so this is still section 5.1. They do volumes in 5.1 also. This is called the solid of revolution, or volume of the solid. Still section 5.1. Okay. What, Saad? What expression? What expression were you talking about?
I was talking about the last question. The area towards the left of the y-axis. Wouldn't that be like considering the area that's below the x-axis when you're taking, when you're calculating area vertically with vertical rectangles?
If I do it right like that?
Yeah.
For this problem?
Yeah.
So
wouldn't the area to the left of the y-axis be considered as if it was similar to when you take the area below the x-axis? So this gives us a net area instead of the total area?
Yes, it would. Yeah, you're talking about this area, right?
Mm-hmm.
Yeah, that would. It would give you, no, it wouldn't, Saad. It would not give you net area. No, because when you do top minus bottom, so for instance, Saad, imagine, and for everybody else, you don't have to listen if this confuses you. Imagine this rectangle. This y value, imagine, is 5, okay? And imagine that this y value is -3. Just imagine. When you do 5 minus -3, what do you get?
8.
That's a positive quantity, isn't it?
Oh, yeah. Okay.
So you wouldn't.
Okay, I understand.
You get area. You don't get net area.
All right. Thank you.
Okay. All right. So let me tell you here. Yeah, Angel.
So like I was looking at the homework, and for some of them, that's what I was like tripping about, because like on some of them, like it gives you x equals and then whatever, but then on some of the other questions it gives you y equals. Is it going to be similar to that, like on the test?
For what? For section 5.1?
Yeah, the homework was like y equals
Right.
something,
So
and then x equals something.
Gotcha. If they give you y equal to already, then they are actually doing the step for you.
Okay.
Yeah.
But for us, we're gonna have to figure it out.
Yup. Most likely, yeah. Yep. Just
Okay,
like
cool.
these questions. Okay, so here is what's going on, guys. We are gonna be learning how to, yes, Noah, it would say. We're not just getting a integral that gives you net area in general. These are area of positive regions. Yeah. So finally, we are gonna be learning about volume. How do you find, and this is a topic that can be done in a day, and it can be learned in a day, honestly. That's why it's left to last. It's typically easier than everything else we'll learn, okay? How do you find the volume of a, for instance, sphere, okay? 4/3, what is it? 4/3 pi r cubed. How do you find that? How do you do the geometry? Well, the question is, how do we construct a sphere or a ball? Not a sphere, but a ball. To create a ball, what we do is we take a semicircle. This is a semicircle. Or the region bounded by the semicircle, this region. And we are gonna revolve that. Can you guys see it? And we're gonna revolve this around the x-axis. If I were to revolve, let's just stick with the semicircle. If I were to revolve a semicircle around the x-axis, it will create a sphere, doesn't it, guys? We'll get a sphere. That's how you create a sphere. Take a semicircle and revolve, okay? And that revolution allows us to find volume. Let me show you how. I actually have a little demonstration here for you. And I just discovered this last night and I didn't play around with it much to learn how it works. But can you guys see that? Yeah?
Mm-hmm.
Okay, so here we have the graph of a half parabola. That graph. And so here the view is a little change. This is the top view of the half parabola. Half parabola. That's your x-axis, your y-axis. And I'm gonna tilt this so you can actually see it from the side. Okay, but this is just a flat plane with a half parabola that goes from 0 to 10. The x value here goes from 0 to 10. And what we're gonna do is we are gonna revolve that curve around the x-axis. Just imagine what happens if that thing is revolved around the x-axis. It's gonna create a ball. The surface will be a ball. And here it goes. Let's see, there we go. So that's going around the x-axis. And look at that surface. The surface is a ball. Okay, this is actually called a paraboloid. A paraboloid is a three-dimensional version of a parabola. Okay, but it's like a ball or a antenna. You know, the inside of it is like an antenna dish, something like that. So the question is, how do you find the volume of this thing? That's what we want to do. Find the volume. So what we'll do is we'll slice the solid up. Let me reset. Okay. And do that. Okay, let me revolve around again. There we go. We're gonna slice the solid up. Let me see if I can show a slice of it here. There. Okay. And let me move this up. So this is a slice slice of a solid. Just cut the solid, take a slice out. You could make that slice thicker. You can make it thin, like that. And what we do is we're gonna find the volume of that slice, okay? Find the volume of that slice and add them up, because this paraboloid, this three-dimensional solid, it consists of infinitely many slices. Not that, but let me see. It consists of infinitely many slices put together. Look at that. So this is the paraboloid sliced up all over. Look at that. Y'all see those slices? Just messed up the little program. Yeah, it's not doing a great job. But find the volume of those slices and add them up. That's the whole logic behind what we're gonna learn. Froze. It froze. Okay. Let me just change screen. I'll draw it for you. Whoever wrote that thing in GeoGebra, they just did such a great job. Okay, but here's a drawing. And we'll go with square root of x, because square root of x is just so easy to comprehend. And let's say 1, 2, 4. Let me do that again. So that's y equal to square root x. Or you know what, let's call it whatever. Let's just call it y equal to f of x. Let me generalize, okay? And it's going from whatever to whatever, a to b. Let's just say 0 to 4 for now. So what we do is we take the region bounded by the graph and the x-axis, that region, and revolve the whole thing around the x-axis. The x-axis called here the axis of revolution. When you revolve that around, as we saw, it generates what we call a solid of revolution, or a paraboloid, giving you a sense of 3D here. Okay, so that's the solid of revolution, not a surface. It's a solid. It's solid because I revolve the whole region around. So all both the boundary and every crap in between revolves around, and it generates the solid. And again, we want to find the volume of the solid. So we take a cross section. Again, cut this thing out, take a slice out. Let me focus on a slice. Okay, so that slice itself is a solid. Okay, I'm gonna extract that slice out and write it, draw it over here. The idea is super easy, man, trust me. Easier probably than areas. Okay, so if you pay attention to the slice, this slice happens to be basically a cylinder. It's a cylinder with a tiny thickness. Okay, the thickness of the cylinder is dx. Why is it dx? Well, that's because this is a small change in x. So we call that dx, right? This is a small right circular cylinder. So if you want to find its area volume, you have to know the radius. Okay, since this is the x-axis is the same thing as, guys, it's the same thing as y equal to 0. The equation of the x-axis is y. At the x-axis, every y is 0. Okay, now if I want to find the radius of this thing, the radius is the distance between the y-axis and the curve. That distance is the same thing as the y value. It's same thing as y. Okay, look at that. That point, this point is on the graph of y equal to f of x, isn't it? That point is on the graph y equal to f of x. So if I'm finding the radius of the cylinder, I just do f of x minus 0, or just f of x. Let me move this down here. Let's make it a little bigger. This is r. R is the difference between f of x and 0. It's, again, think of it as the top y minus the bottom y. This equation minus this equation, which is just f of x. That's a radius. So we can now find the volume of this tiny cylinder. We call that dV. dV is an increment of volume, or just the volume of a tiny slice. And since it's a cylinder, volume is pi times r squared times height. Okay, height is just dx, or delta x. Again, pi r squared times the altitude, or height, altitude, delta x. Here r is the same as f of x, so our dv is pi times f of x squared times dx, pi r squared. Okay, and if you want to find the total volume, well, what you're going to do is you're going to add up the volume of all slices. Adding up means Riemann sum. Riemann sum means definite integral. Okay, so here v is equal to the integral from a to b of pi times the square of f of x. And let me just leave that in blue. Times the thickness dx. And you can take the pi out because pi is a constant, but this is called volume using the disk method. The disk method. Why is it called the disk method? Because this thing, the surface of this cylinder is just a disk. Okay, this here is a disk. Okay. Now, a lot of people memorize the formulas. I don't want you to memorize things. I want you to derive them. Please do not memorize this formula, okay? I mean, it's good to understand it, but when it comes to applications, I want you to actually derive the formula on your own. The reason for that is because the axis of revolution, this axis is not always y equal to 0. And if it's not y equal to 0, then you have to do f of x minus whatever that number is. And trying to memorize that formula and variations of it is not easy. Okay, so let's see. Let's begin with, yes, let's begin with the volume of a sphere. Finally, we can derive the volume of a sphere. Of radius, let's say radius is a. Okay, so how do we do this? We take, again, as I said, we take a semicircle and we revolve around the x-axis. Just try to make it simple. So here let f of x equal to square root of a squared minus x squared. This is a semicircle of radius a. Okay, so here is negative a, here is a, and this is that semicircle. It looks more like a half a semi-ellipse. Hold on. Whatever. Okay, so that's the function. And again, all you got to do is revolve this around the x-axis. You could have also taken a semicircle like that. You could take the right semicircle, the equation of it would be a squared minus y squared, actually. And revolve that around the y-axis. Nobody cares. It's just the same thing. So revolve this around, and you end up with the sphere. Okay, so again, let me just do this. This is the function. And it's revolve around. Let me erase this thing. Okay, so change that to green. Okay, so what we do is we take a cross section of this thing. But this is the cross section. Imagine you have a tennis ball. You're cutting your tennis ball, or a loaf of bread, whatever. You're just taking out a slice like that. Okay? That's it. All right. So, main question here is, what is the radius of this disk? This is a disk. We want to know the radius of it. The radius is always any distance that you're finding. It's always either top minus bottom or right minus left. Okay, so again, on top right here, this top y is y equal to square root of a squared minus x squared. Okay, and the bottom y, the center of this radius, center is just y equal to 0. Okay, Therefore, the radius here is equal to the top function minus the bottom function, minus 0. So here radius is just square root of a squared minus x squared. If the axis of revolution was something else, if you were revolving this around y equal to 1, then this would have been y minus 1. That the book doesn't do this. The book doesn't say do that minus that. They don't. And then they later go with a different axis of revolution, an axis other than 0, and that can confuse people. So I'm doing it this way: top minus bottom. Bottom is that. So that's the radius of this disk. Again, dv here is pi times radius squared times the thickness of the cylinder, dx. Plug it all in. Pi here, r is square root of a squared minus x squared. We're squaring that, multiplying by dx. So let's just simplify that a little bit. You have pi times a squared minus x squared. The squared kills the square root, thankfully. And now you're doing the integral of that. Okay, so your volume is equal to the integral from, look at all these disks or cylinders. They all begin from with negative a. So we have all these disks stacked up. All of them stacked up. And you're adding the volume of all of those, which is the same as the integral from negative a to a of pi times a squared minus x squared dx. And guess what? We can totally use symmetry. Just do the double of the integral from 0 to a, and you can take the pi out. So 2 pi integral from 0 to a. Okay, find the antiderivative. Gotta be careful, guys, because the antiderivative of a squared, the integration is with respect to x. So the antiderivative of a squared is not a cubed over 3 or 1/3 a cubed. Here a is a constant. A squared is a constant. And we know that the integral or antiderivative of a constant is constant times x. So antiderivative of a squared is just a squared times x. Imagine a is 3. So that whole thing would be 9. Antiderivative of 9 is 9x. Minus, now the antiderivative of x cubed is 1/3 x cubed. Going from 0 to a, we get 2 pi times a squared. Plug a in, so you get a minus 1/3, plug a in, you get a cubed. Okay, so that's when you evaluate the antiderivative at the top limit. Now evaluate at the bottom limit, but when I plug 0 in here, everything zeroes out. So we get 2 pi times a squared times a cubed minus 1/3 a cubed. Almost. 2 pi. A cubed, take a third out. 1, take a third out. You got 2/3. 2/3 a cubed. Okay. Multiply 2 by 2. You got 4 over 3 pi a cubed. Cubic unit. And that was expected. Volume of a sphere is 4/3 pi radius cubed. Radius here is a. So do you think in the beginning they found a volume for a sphere like that? No. They used simpler geometry. Yeah, we couldn't have done this. I don't know. Doing a derivation of the volume for a sphere and using basic geometry. I don't know. Have you guys seen it? I haven't. I really haven't looked at where volume of a sphere comes from. I haven't done the basic math to see where it comes from, but this tells you where it comes from. We just did it. We just derived it.
Yeah, our teachers always make us memorize it. Huh.
Yeah, well, yeah, I mean, yeah, you're right. We memorize it. We have it in our memory, but where does it come from is the question. Don't you always ask, oh, why is slope equal to m? Why is the volume of a cone that? I mean, you wonder, right? So now you know where it comes from. Okay, let's do more. Yeah, so let's actually change the axes of revolution. Hold on, let me see what kind of problems you guys have in the book. All right.
There's one part kind of have a
Which
question.
part?
So why are we changing the interval if you're gonna be taking the integral of the whole thing from -a to a? Like, why are we taking the 2 pi out?
Well, first of all, okay, the pi is from here, right?
Mhm.
That I took out. Now, the question is why 2? You can find a volume of half ball and double it, can't you? I found the volume of the semi-sphere, that, and I doubled it.
Okay,
But,
I'll do it then.
yeah, instead of doing the integral from -a to a, I just did the integral from 0 to a, and I doubled it to get the full sphere.
And that's what the 2's for.
Yeah, that's where the 2 comes from.
Okay. Okay.
So do volume from 0 to a. So this would be a hemisphere. And double. You don't have to do that. It's just easier because if I were to do from -a to a, from -a to a, it would be a pain in the neck to plug -a in here. You know what I mean? Just want to be clever with the amount of calculation that you have to do. All right, so let's see. Okay, let me see if I should change my region. Let's go with let's begin with the simpler example here. So let's say that we are gonna go with the region here. It's bounded by graph of y equal to square root of x. Let's go back to square root of x. Okay. The x-axis and the line x equal to, let's say, 4. Let me draw the region. Okay, so square root at 4, it's 2. Square root of 1 is 1. Here's a graph of the square root. And then x equal to 4 is this line right here. It's a vertical line. I'm just gonna make it dashed. Okay, and the x-axis is this right there. So we have our region. That's our region. We are not finding area, guys. We are finding the volume. Okay, and let me just copy and paste this graph because I'm gonna use it again. And let's just say that region, the region is going around again, going around the x-axis. If it's going around the x-axis, there is nothing interesting going on, right? So let's make it go around a different axis. Let's revolve this around. Let me see, what would be a good example here? I don't want to make it too complex before the closing of the day. Hang on a second, guys. Let me just think. Just want to do something easier. Okay. Let's say we make it go around x equal to 4. Yeah. Do I want to do that too? No, I don't want to do that. That's also difficult. Okay, let me think of something else. This is why you should prep your lecture notes before you teach. So give me a moment. Let me think for a second here. All right, we'll make it go around. We'll make it go around x equal to -1. Okay, so this is the axis of revolution. Going around that line. All right. I want you guys to think about the kind of solid that is created. The solid that when the region goes around, there is no longer a disk. There is a massive hole. You all see that hole right there? There's gonna be an empty space, total emptiness. Okay, so if I could.
Professor.
Yes.
Around y equal -1 or x equal?
Y equal to -1. Thank you. That's y equal to -1. Okay, I'm just doing my best to graph these. Yeah, going around y equal to -1. So when it goes around, there's going to be, because of the gap between this boundary and the axis of revolution, there is an area of emptiness or a hole right there. So when you now take a slice, let me see if I can give this a sense of 3D. Here's that hole. And look at that, guys. This is not a disk anymore because of the hole. This is called washer. The cross section is a washer. Okay, I am going to draw a washer here also. A washer is a disk with a hole right in the middle, like that. Washer. You guys can see that, right? Okay. And again, there is a thickness to that washer. That thickness, just like before, is dx. So the thickness didn't change, just dx. All right. Now, let me draw that washer out here. So that we can find its volume. So the thickness. All right. So begin by labeling the center of that washer. The center is y equal to -1. Okay? Yeah. Now, this point on the washer, that point is on the graph of y equal to, this is y equal to square root of x. Right? This point on the washer, that point is on the graph of y equal to root x. Okay? This point on the washer, this right here, is on the x-axis. This is on y equal, where the whole begins is on y equal to 0. That's the equation of the x-axis. Okay, so if I have those three quantities, then I am able to find the volume easily. Okay, so how do you find the volume of this washer? Well, find the volume of the whole thing as if there is no hole. That would be the disk. And then subtract the volume of that hole. That's what you do. You just have to take this out. Okay, so it's going to be V big minus V small. Okay, bigger volume minus the smaller volume. Okay, to find a bigger volume, and I'm running out of time. Let's just finish tomorrow. I don't want to go over time, but this should give, we'll just continue tomorrow, okay? So just think about this picture for a little bit. I don't want to burden you with more information. I see you tomorrow.
Thank you, Professor.
Welcome.